everybody for coming tonight. I'm Jason Evans. Some people have actually asked me whether I work at Facebook. I should make it clear I do work at Facebook. I've been here for the last year or so, working a lot on jemalloc, which is a kind of a long-term project of mine. I'm going to tell you some of what we've been doing with jemalloc over the last year and a half here at Facebook, how we've been applying it to our various applications. The talk is going to be broken down into 5 major components here. I'm going to give you a little bit of history and background on what malloc is, how we're using it at Facebook, kind of the constraints that we're working under. Going to give you some background on how jemalloc currently works, and then talk about some of the innovations in jemalloc since adapting it to Facebook's workloads. The algorithms and data structure section is going to incorporate those innovations, so you don't need to forget anything about what I just told you once we get to the innovations. I'm going to show you a couple of real-world benchmarks based on some of our server loads here at Facebook, and then talk a little bit about some ways we might be able to improve the allocator moving forward. Okay, so getting right into the background. So what is, I just hit a button, I'm not sure, hopefully nothing bad happens. What is malloc? Those of us who program at a low level, I tend to do a lot of low-end, kind of back-end sort of work, and so this is a common interface for me. A lot of us that are working at a higher level language kind of forget about this after a while. Malloc really is these 4 functions. There have been some additional things that have been bolted on the side, but this is really the gist of it. Malloc, you ask for some number of bytes of memory. You don't tell the allocator what you're going to use it for. All you say is, I need this many bytes. Please give me at least this many, and I'll give it back to you sometime if I feel like it. On the other end, we've got free, where you deallocate that memory, say, okay, I'm done with it. You can do whatever you want with. You know, the allocator is free to repurpose it for however it sees fit. And then there are a couple of other interfaces, calloc, which is similar to malloc, where it's zeroed memory, and reallocation, where you're expanding or contracting an existing allocation. So I started on this project in about 2005. It was part of a research project. I was implementing a language runtime for scientific computing, and I thought I needed a memory allocator for the garbage collection strategy, and spent a few hundred hours implementing that, and realized I didn't really need it and didn't want to waste all that effort, so I integrated it into FreeBSD so at least somebody would be able to use it. And that was kind of the beginning of the end as far as this project goes. You know, a few hundred hours of effort couldn't possibly waste that, and it's been thousands of hours since, and it just keeps going. It's a much more intricate problem than I ever guessed when I started on this. So when it first went into FreeBSD, it solved the thread scalability problem. With multi-CPU systems, there's a problem with locking. You have to be really careful to avoid synchronization bottlenecks. And it solved that problem, but it had a lot of fragmentation issues. And so right off the bat, I had to rewrite the core layout algorithms in order to improve the fragmentation behavior. Made a lot of incremental improvements over the next couple of years. And then in 2008, worked with some engineers at Mozilla to integrate it into Firefox 3, basically replacing the Windows memory allocator, which has some horrible fragmentation characteristics. I'm told that's been fixed since in the latest version of Windows, but it certainly was a problem back then. The main topic of this talk is really going to be what I've done with jemalloc at Facebook over the last year and a half or so. Facebook's applications, the server applications, really have different constraints than a typical desktop application that we work with. You know, even a heavyweight thing like a web browser, which uses hundreds of megabytes of memory, maybe even a gigabyte of memory, is nowhere near kind of the typical way that we use a machine. Here, we have 8 or more CPUs in each of these machines, have 8 or more gigabytes of RAM, and that's a use it or lose it resource. And so, given all this memory, we try to use every last bit of it to get whatever speed benefit we can from that resource. That has some impacts on how the memory allocator really is going to behave. If the allocator is using kind of quadratic algorithms for the way it stores its internals, things are really going to head south quickly. And in fact, we've seen a lot of that with the default system allocator, glibc, with a lot of our projects. So a year ago, we were using kind of a blend of tcmalloc and jemalloc for our applications, where tcmalloc was really doing a good job for us from a speed and introspection perspective, and the introspection was really a key component of how we were using it, being able to diagnose problems with memory, whether it's memory leaks or memory errors, whatever, at a large scale. When you're talking about gigabytes of memory, it's important to be able to do heap profiling and whatnot. And TC-malloc did a great job of that, but it had fragmentation problems for some of our applications. And so we're caught where we'd have to ship a production binary using jemalloc, but anytime something went wrong, we had to back up, build a different version of it with jemalloc or with TC-malloc, figure out the problem, and then go back to jemalloc again. That was really not ideal, and so we needed to kind of blend these features. And of course, being that I wrote jemalloc, I chose to do it to jemalloc rather than TC-malloc. Okay, so first, before we get into the guts of jemalloc, I need to go over a few terms. These first four terms are kind of related. They're nested. Arenas manage chunks, which contain runs of pages, page runs, and those in turn can contain regions. So going back to the top, an arena is a completely disjoint allocator. It's possible to have multiple arenas in the application operating at the same time, and they don't impact each other at all. So they can be running completely concurrently. This is the main strategy that jemalloc started off using for concurrency, for scalability. Now, those arenas manage chunks internally, and by default, chunks are composed of, they're 1,024 contiguous pages, 4 megabytes. Notice it's a power of 2. That's actually important in that everything is aligned on 4 megabyte boundaries. And this allows us to look at a pointer, look at the lower order bits on the pointer, and tell whether the pointer is to the base of a chunk or whether it's somewhere internal to the chunk. And I'll show you some diagrams later that make this more clear. A page run is some number of pages within one of those chunks, and then the page runs themselves can be broken up into regions for small allocations. Okay, another term that we need to go over quickly is a dirty page, specifically an unused dirty page. When the allocator asks for virtual memory from the operating system, that starts off untouched memory. In fact, there's not even a physical page of memory associated with that virtual memory yet. As soon as the application touches that memory, it's then dirty, but it's active, it's being used. At some point, that page may become unused. Everything, all the active data inside of that page is no longer in use. So now we've got this unused dirty page. We allow those to accumulate up to a degree, basically because it's kind of expensive to throw them away and then go get some more memory. But if too many of them accumulate, then it really impacts the total footprint of the application. So there's dirty page purging that's built into jemalloc. And so when I talk about an unused dirty page or dirty page purging, this is what I'm talking about. Okay, into how jemalloc works, why it works. The first thing, and probably the most important aspect of jemalloc's policies that really explain why it works as well as it does from a fragmentation perspective, is how it chooses which regions of memory to use. Given a choice, say you're allocating a 16-byte object and there are a number of regions available in memory, jemalloc always tries to use the one that's lowest in memory. The reason for that is that it allows the application to kind of its working set ends up packed low in memory. So there may be some fragmentation. There's going to be fragmentation everywhere, but the fragmentation is going to be less. It's going to tend to be less in the low end of memory. And as the application's memory usage fluctuates up and down, it's possible for those high pages to completely drain. And that actually allows us to more effectively purge those pages at some point and really reduce the footprint of the application. Any stable ordering would work. You could use high addresses preferentially. You could probably come up with something else, although it'd start getting harder to implement something that's a stable ordering. Now, there are a couple of exceptions to this policy for jemalloc. Unfortunately, arenas and thread caches, which are both concurrency mechanisms, kind of inhibit our ability to do this universally. So there are some exceptions to this, but whenever possible, jemalloc does in fact choose low addresses. Another aspect of fragmentation avoidance is size class choice. You could imagine a couple of extremes for size class choice. One might be powers of 2. The problem with that is, imagine you allocate a 513-byte object. You really get 1 kilobyte, so you've wasted almost half of that memory to internal fragmentation. And it's not all that uncommon to have objects that happen to be just slightly over some size class limit. In practice, that works pretty well, better than you might expect. This is what phkmalloc, the predecessor to jemalloc and FreeBSD, did, and it got everything else right, and so this really didn't impact it too badly. It was one of the best in existence in terms of fragmentation at the time. So at the other extreme, you might choose to have size classes at every quantum, and you'd have a whole pile of size classes. And the problem with that is some of those size classes are going to tend to be underutilized, and the memory is just locked up for those size classes where it could be used for something else, and that tends to increase the fragmentation of the application. So I'll talk more about large and huge objects later, but you can see the the small size classes there. I think it adds up to 28 size classes, I think. The spacing kind of broadens as we get closer to one page in size. Now, in an ideal world, we wouldn't devote any of our memory to the metadata for the allocator, but that's not possible in practice, of course. And there are really two major sources of overhead for the allocator. The primary one is the arena chunk header overhead. Now these chunks are 4 megabytes, and the first 4 pages of these chunks are just pure overhead in terms of accounting. That's about 0.8% of memory. And then also we have small page run headers, which you'll see in a diagram in a little bit. They could be, in theory, as much as 1.5% of memory, but in practice it's much less than that. So the total overhead for jemalloc tends to be around 1, maybe 1.5% at the high end. In addition to minimizing metadata overhead, it's important to store the metadata compactly. So if there's a free page of memory, it's really a bad idea to store a linked list that incorporates that page, where that's the only thing being stored on the page. You really want to be able to just completely discard that page at some point. And also, I mentioned this a little bit ago, it's really a nice property if you can pack all of the application data as close together as possible. So having headers on every object, which is a technique that a lot of allocators use, really decreases application locality, especially if you've got an application that does a bunch of does all its allocation, then goes and does its work. If you're going in and out of the allocator all the time, this is not as big of a deal. But this is the main topic that we've probably seen so much in the literature over the past 10 years in terms of memory allocators. How do you avoid synchronization overhead? Back in the dark ages when we first started doing multi-threading on single processor systems, the solution was slap a global mutex on the entire allocator. And that works fine under those conditions, but as you add CPUs, it quickly breaks down. So jemalloc started off solving this problem by having multiple arenas. Like I mentioned earlier, these are disjoint mutexes. The arenas can operate completely independently of each other, and in practice, the mutexes are almost never contested. Well, even better is to completely avoid synchronization. And tcmalloc, the Google Perf Tools allocator, took this approach and was really the pioneer here, and it works great. And this is something that jemalloc has also started doing over, I guess, maybe 2 or 3 years ago I added this. A little bit about allocator philosophy before I go on. I really have tried to make jemalloc general purpose and as simple as possible in kind of a strange way. There's a lot of complexity if you look at the jemalloc source code, but in the important ways, which I mentioned, memory layout algorithms, trying to pack things as low in memory as possible. If we were to use some more sophisticated layout policies, it becomes really difficult to reason about what the application does over time. And so when fragmentation occurs, who knows why? It's every little heuristic tweak that's added to the policy makes it that much harder to reason about the allocator. So yes, jemalloc, like every other allocator in existence, does have some worst case behaviors. It's possible to construct inputs that make it lose its mind. In practice, I haven't really seen it, but it is possible to do that. But when it happens, we want to know how performance is going to degrade and make sure that it's going to degrade gracefully instead of falling off of a cliff. Okay, I've got 2 slides showing kind of the internals, the memory layout and data structures, and then we're going to move on to the next section of the talk. So first, here's an arena chunk, and it's a 4 megabyte region of memory. At the beginning comes a 4-page header, and you can see a blow up of the header on the right side of the slide. A little bit of metadata followed by a map which describes what all of the pages within the chunk contain. Now let's switch back to the center here for a moment. You can see there are 4 different page runs inside of this chunk, the 4 major types of them. There are large runs, small runs, which back small objects, the small regions. You can see down there a blow up of the small run. It's got a little bit of header data at the beginning, followed by the regions that can be allocated individually. Then there are a couple of different unallocated run types as well, dirty and clean, and I'll talk about that just a little bit more in a moment. So the way that you would, say you wanted to free an object that was allocated inside of this small run, the allocator, what it does is it masks off the low order bits. It finds the entry within the map for that page and figures out, oh, it's inside of this small run. It's maybe, say, the page offset 1 within this 3-page run. Therefore, the metadata is going to be at the beginning of the previous page, and it's able to look up all the information it needs in order to do the deallocation that way. Okay, last one here. I'm going to go into a couple of relatively detailed examples of how jemalloc works, just because I think it's going to be useful for you to understand kind of how jemalloc works in a nutshell as far as how the thread caches and arenas interact. I've got an example here with 3 threads that are currently in existence. Once upon a time there was also a thread B, but right now there's just threads A, C, and D. As they did their first allocations, they were assigned to arenas 0 through 3, and those arenas all still exist. We're going to focus on thread A and arena A, of course. It's got a thread cache represented in the top right-hand corner. So if we were to allocate a 192-byte object, we would find the appropriate bin in the thread cache, which is bin 9 here, and check, are there any available objects? In this case, we do have a couple of available objects, and so this is the fast path for allocation. We just pop one of those off of this stack of free objects, and we're done. Supposing that the cache, the available cache, were empty for this size class, instead we'd have to do a bulk allocation. We'd allocate, I think it's 63 objects for this particular size class. I don't remember exactly. But we'd end up having to go into the arena, though. So we'd look for, again, we'd look for the appropriate bin, which is bin 9, lock that bin, and then look in a red-black tree to find the lowest run in memory for this arena that has available space in it. And so you see here there's a run cur and there's a runs. The runs data structure is a red-black tree, and the minimum in that tree is the current run. There are 57 free objects here, and so we bulk allocate a bunch of those. That's not going to be quite enough, so we have to go get another run out of the red-black tree and finish up bulk allocating. Once that's done, release the lock. All of those objects are now in the thread cache, and we can pop one off. Okay, so that's how small allocation works. There's some similar caching that goes on for objects up to 32 kilobytes by default. So you can see those T-bins 28 through 35. Those are for large objects. Let's see. I guess I also want to give you an example of how that large allocation occurs if it's not cached. So let's say we're doing a 64 kilobyte allocation. The thread will look in the arena, it will lock the arena, and then check these runs avail trees. It'll first look in the dirty tree, trying to reuse some unused dirty pages, because those ones have already been backed by the kernel. And if it fails there, if there's nothing large enough in that red-black tree, it checks the clean tree. If there's nothing there, then we have to go allocate another chunk, insert it into the clean available runs tree, and then we can allocate. We actually succeed and get our 64 kilobyte object. Okay, so I hope you more or less followed me through that. There's a lot of complexity this tries to capture, so you might benefit from looking at this later on in the blog post I put up. There are also some simplifications here. One of the important things to note is I'm only showing us operating on Arena 0 here, so the thread cache has chains of free objects that are all inside of Arena 0, but threads can pass objects between each other, so thread A may be freeing an object that was actually allocated by C. When that happens, it does in fact get inserted into the thread cache. So it doesn't immediately go back to the arena that it came from, but when full deallocation, where it gets flushed from the thread cache, when that actually occurs, it goes to the arena that it came from. So it can live for some arbitrary amount of time in a thread cache, not associated with the arena that it came from, but it always goes back to the original arena when it does get deallocated. Okay, we're going to get into some of the Facebook innovations. The first thing we had to do is make jemalloc faster. So I work on a project called HPHP, which is a compiler that converts PHP code to C++ code. We use this to build up a huge binary of our website. We ship that out to our web servers, and that's how we serve our web traffic. Well, this is a pretty large-scale operation, and a few percent performance actually matters. And so jemalloc had to be at least as fast as tcmalloc in order for us to be able to justify using it in this environment. So I had to make a bunch of changes, and the first of these really one of the largest impact ones, was the thread cache rewrite. The old thread cache used arrays of pointers to store which, these freed objects, the ones that are cached, and there were some problems with that. The first is, for the large size classes, say 3 kilobyte objects, it would fill an entire magazine the first time you tried to do an allocation of that size. And so, say that magazines stored 60 some objects, and these are 3 kilobyte objects. You're talking about 180 kilobytes. Right off the bat, the first time you allocate. So there's a real problem with the sizing of the thread cache, and also objects could languish in the thread cache indefinitely. So we solved this in 2 ways. First off, the thread cache, it's using singly linked lists, as you saw on the previous slide, but also we've limited the total number of objects that can be cached for each size class, so that as the sizes increase, the total number of objects that can be cached decreases. And this kind of keeps the thread cache more even as far as its memory usage across the different size classes. And then also, I'm going to use this term incremental garbage collection. I know that has some connotations that may be confusing, so really think of this as cache expiration. If an object sits around in the thread cache for a couple passes of this garbage collection sweeping, then it gets expired out. And the way that happens is every so many allocation events, one of the bins is checked to see, have these objects all been used since the last pass? If not, let's purge 3/4 of the ones, expire them out of the cache, so that they don't sit there taking up memory indefinitely. This is important for fragmentation primarily, and also memory usage in general. These caches can get pretty large. The strategy is pretty simple for jemalloc as far as how the thread cache is sized. There's not an upper limit on the thread cache size, just other than in terms of the maximum number of objects of each size that can be cached. We made some pretty major changes to how jemalloc performs locking. Back in the beginning, and in fact until not too long ago, about a year ago, jemalloc used 1 mutex per arena, and during the entire duration of any operation involving an arena, that mutex was locked. And we noticed, given the volume of allocations we were doing, that threads were queuing up behind this mutex waiting for system calls to complete. So when we're doing this dirty page purging that I was talking about a little bit ago, this can take a while. You're just doing a system call. And so all these threads that are really doing unrelated operations would just be sitting there waiting for that mutex. And so we first pushed down the mutexes into the bins so that it's possible to do a small memory allocation at the same time as something kind of at the higher level, at the arena level for page run operations was occurring, whether it be dirty page purging or whatever. That was a definite improvement, but it wasn't good enough. We were still running into serialization problems. And so we modified the code so that all the mutexes are dropped during the system calls. So it doesn't really matter if a thread takes forever to do all this dirty page purging. Other threads can keep on operating regardless. And this really, between these 2 changes, really solves the synchronization bottleneck for the arenas. We also modified how dirty page purging works pretty substantially. It used to be that there was a fixed threshold. I think it was 512 pages per arena. And once that threshold was reached, then some number of those pages, I think half of them would be purged. And the idea was, sweeping downward through memory, the dirty pages would tend to be low down, and since jemalloc prefers low addresses during allocation, it would tend to be reusing the dirty pages. This had a couple of problems in that it's expensive to sweep down through these chunks repeatedly. You've got to traverse those chunk data structures and find the dirty pages. So there was not I guess at some level it's a constant time operation, but the constants are pretty big. And the other problem is that if you're repeatedly purging the chunks that are high in memory, the dirty pages, the dirty unused pages, are going to tend to be kind of sparse. And so you have to make a lot of system calls because you're doing 1 page here, 1 page there. Whereas if you wait a while to do the purging for a particular chunk, you'll tend to get some coalescing of the dirty pages, and you can purge 20 pages at a time on average. And in fact, I think that's really what the number tends to be. When I've been looking at the statistics, 25 pages or more on average for each system call. So that reduces the total number of system calls. It also has some real benefits in that we segregated the dirty and clean available runs. Didn't used to be that way. There was just 1 tree for all the available runs. By segregating them and preferring the dirty pages, we made much more effective use of the existing dirty pages and reduces the total amount of dirty purging that has to go on. And I'm just going to mention this very briefly. JMalloc's on its 4th red black tree implementation. The yeah, it's one of those things. I really hope I never write another one. The first two, one of them was my own implementation, a straight translation of the algorithm that's, I think, in the Rivest et al. Book, Common Data Structures Algorithms book. It's a great book. That's a really fast, it's a fast implementation, but it uses parent pointers and stores, you know, there's an extra field for the color. And that wastes a lot of time. I showed you with the chunks, we're using 4 pages for every one of these chunks for metadata. Well, if we were to have nodes where had all 4 of those fields, parent, left, right, and color, then that would almost double the size of these chunk headers. So JMalloc's red-black trees only have a left and a right pointer, and the color is stored as the least significant bit in the right child. So that's not as fast as kind of the optimal implementation where you actually have parent pointers, but still this is 30% faster than what I had before, and it's, I think, good enough. It's the right trade-off in terms of time and space. We improved introspection of JMalloc in a couple of ways. I'm going to talk about heap profiling in a little bit more detail in a moment, but the other thing we did is extend the kind of the internal statistics mechanisms. JMalloc has always been able to dump a bunch of statistics about what the allocator did over the lifetime of the application, but it would only do that at program exit, and that's pretty useless for a server application that runs indefinitely. So we modified it so the application could call this function repeatedly, but it's human readable still, and we wanted to be able to automatically aggregate these statistics, store them in databases, whatever, pick just the ones we care about. And there are a lot of reasons we wanted to be able to access these individually. And so I created this malcodal interface, which is really based on the BSD syscodal system call interface. It's a very similar mechanism. And you can get at all these different statistics, and we also use it for miscellaneous controls like thread cache flushing. You can call malcodal tcache.flush and with some null parameters and whatever, and it'll flush the cache for the calling thread. And there are a number of other mechanisms like that, not all of which are listed here. So,
how often do you find you're using these tunables?
So I guess I should say, I think they're going to pass mics around for questions afterwards. I'll go ahead and answer your question. Your question was, how often do we use the tunables? So you're talking about like the thread cache flushing, arena purging. You know, it kind of varies by application. The thread cache flushing one is one that we actually actively make use of right now. The arenas purging one is more, I think I'd say it's more useful for kind of experimentation, trying to figure out how big of an impact is this dirty, the dirty page accumulation actually having, what kind of performance hit does it impart, and could we tune the amount of dirty pages that we're willing to let sit around, that sort of stuff. So a lot of these interfaces are useful for development. You'll see at least one more mentioned later in the talk. Okay, so heap profiling. I don't know how many of you have used this in the context of jemalloc or tcmalloc, but those of you who haven't, please do. This is a wonderful, wonderful facility. tcmalloc totally nailed this, and we essentially did the same thing. It's a mechanism for statistically sampling all the allocations that occur, getting a representative indication of where memory is being spent. And there are a lot of facilities you can take these dumps on a regular basis, kind of at program termination, whatever. You can look at memory growth over time, figure out where leaks are. It's really, really useful. There are a couple of things that we did that the tcmalloc doesn't currently do, like jemalloc it does current and cumulative statistics, whereas tcmalloc only tracks the current statistics. This has a memory impact as far as how much metadata has to be stored internally, and so we can optionally disable that in jemalloc, but I think that is one difference between the two. There are a bunch of different ways of triggering the profile dumps. In practice, I think we find that the manual triggering is the most useful, just because it's nice to be able to trigger, say, every minute or every 5 minutes, at particular points during application execution. These other mechanisms are really meant more where you don't have the ability to easily add the calls into your application. Here's an example of what the output looks like, just to kind of whet your appetite. I ran the W program, what, and at program termination, it dumped a heap profile, and you can see the top users of memory are the 325 function and this NSS LDAP whatever function. You can see that the total amount of percentage of memory that they're using, cumulative. There are a bunch of statistics there. On the right side, you can see a full call graph of where those occur. and the larger nodes in the graph are the ones that are using the most memory. There are a lot of features here that I haven't even touched on, so really go check this out. So we also added a couple of experimental features to jemalloc. This is the first of the two that I'm going to talk about. As solid-state disks become available, it's really tempting to scale an application out such that rather than constraining your total memory usage to the amount of physical RAM, you constrain it to the total amount of space on your solid-state disk. Just treat the RAM as an extra level of cache in the memory hierarchy. This works pretty well as long as your application has a working set that fits in RAM. Not so well otherwise, kind of for similar reasons that if your application doesn't fit in L2 cache, you really see a drop-off in performance. But I think this is really going to be increasingly an enticing option as solid-state disks become cheaper. You know, we're kind of on the cusp of this right now. I think we're going to see increasing use of this for applications at this scale. And then the other thing I wanted to tell you about in terms of experimental features is this new allocation API we came up with. Now, I told you about malloc, calloc, and so on at the beginning of the talk. There's also been POSIX memoline bolted onto the side as a standardized API, and there's also malloc usable size, which tells you, given a pointer, how large is the actual object. The POSIX memoline is really increasingly important for threaded applications because it's important to make sure you don't have any false cache line sharing between threads. So say you've got a 48-byte object and you use the first 3/4 of a cache line and then some other object gets allocated right after that and you're fighting over that cache line, you can really kill performance. You won't have correctness issues, you'll just see horrible performance. And so in that case, you would say, okay, give me something that's 64-byte aligned. Make sure that you actually get the full cache line, so that nothing else is going to impede your performance. You can do that for POSIX memoline, which is the equivalent to malloc. But what about calloc and realloc? Right? It'd be nice to be able to allocate aligned 0 to memory, reallocate aligned memory. And these are cases that actually come up. The aligned realloc is I actually have a use case for this right now. There's some other features in here I'm not going to go into, but the point is that this is actually a smaller API and it does a lot more. I think it has some useful features, especially in a threaded environment. Okay, let's get into some benchmarks here. Before we do that, a couple of tuning tidbits here. If you're going to try this at home, you're not going to get the same results as me unless you do these things. First off, if you're doing C++ application development, make sure you disable the STL suballocators with this environment variable. It's really kind of I guess I can't think of it in any other terms than as a giant memory leak. These suballocators, they cache the memory, they never give it back to malloc, and you can waste hundreds of megabytes of memory, fragment memory. It's kind of a disaster. TCmalloc has turned this off automatically for you for years. jemalloc being a C-based allocator does not do this, but it's really important for C++ application development. Then the other thing is make sure you're using a reasonably modern Linux kernel, just because there's a bottleneck in the page map handling for older versions. Okay, I compared 6 allocators. I tried to do more than that, but none of the other allocators could handle this benchmark or had stability problems, whatever. And I measured hip hop running our web server, actual Facebook website, and I already told you what hip hop is. These machines were all identical, sitting right next to each other in a data center. All of them had 8 CPU cores, 8 gigabytes of RAM, and they had similar, though not identical, request streams. Now this experiment was run over the course of almost an hour, so the minor differences in those request streams really wash out over time. So this is very much an apples to apples comparison where the only difference is the allocator. And here are the results. These are scaled such that bigger bars are better. This is in terms of throughput, and I measured that the kind of the CPU consumed for each request. And so on the right side, you can see jemalloc as the highest, the best performer. TCmalloc not too far behind that, about 4.5% or so behind. That 4.5% actually matters at our scale. But really, what I want you to look at is what if you were using the system allocator, right? You would have thrown away over half of your total throughput. That's really a big deal. So if you're doing heavily multi-threaded application development, it's really important to look into these alternative allocators. should mention ptmalloc is actually what glibc's allocator is based on. So these two, it's not a surprise that they have similar performance. Horde did very poorly in this benchmark. It appeared to be contending on a userland spin lock, probably doing some sort of rebalancing for its blow-up avoidance algorithms. And then Concur, you may not have heard of it. It's an allocator released by Gracenote. They're the people who do CDDB. And it did pretty well, all things considered. It's a pretty, I mean, it's what, 1,200 lines of code or something? You know, for as simple as it is, it really did pretty well. Okay, I did one other experiment here where I disabled some features in jemalloc just to try to get an idea of how they contribute to the overall performance of jemalloc. And the three different things I disabled, in one case I dropped the allocator down to where I was using 1 arena instead of 32. In another case I disabled the thread cache altogether. And then for this last of these I just disabled the garbage collection, the expiration mechanism for the thread cache. Same experimental configuration as previously, 4 machines instead of 6, obviously. But I actually had, I think, 2 hours and 40 minutes of data in this case just to get a little more statistical power. And there are the results. Now, I guess I could tell you that, of course, I expected this, but that's not true. Over on the right side, you can see the default configuration. With the thread cache garbage collection disabled, it's actually about 2% faster. So this is something we're going to dig into some more. When I originally did the performance test 6 months ago, this wasn't true. I think there have been some other changes we've made since then that have had an impact on how our application is running. The other two here, the disabling the multiple arenas and the thread cache, I expected these performance throughput numbers to be reversed. As you can see, with the thread cache disabled, that drops the performance down, what, 4.5%? That's right in the same range as tcmalloc. So jemalloc with no thread cache, just using multiple arenas, performs the same as tcmalloc, which does thread caching as its primary strategy. I really expected the performance to be much worse than that. But on the other hand, I expected the performance with 1 arena but still thread caches to be unaffected, and as you can see, is a big deal. There were a couple of experiments that I didn't put up here just for sake of time, but one possibility would have been to drop the quantum to 8 from 16. jemalloc uses a quantum of 16, really kind of for compliance reasons. For SSE, you have 16-byte registers, and really all the allocators should be using 16-byte quantum. But jemalloc, I think, is just about the only one that actually does. So this has an impact on the total amount of memory that's used. It actually, given the way jemalloc tuned right now, it looks like it slows things down too, which was a surprise to me. And then another experiment that would be really interesting, but would require a lot of different settings, is to kind of vary the maximum size that's cached in the thread cache, and then decrease the number of arenas correspondingly. Maybe find a better setup than what we're using for defaults. Okay, I've got a few anecdotes to share with you. Besides the benchmarks I just showed you, we're using this for a lot of other applications at Facebook, and we've had some pretty impressive improvements with jemalloc. These first two have to do with glibc fragmentation or just data structure scalability, really causing us problems. In the first case here, the logging software, the fragmentation over the course of a day would get us to the point where malloc was taking 30 milliseconds. I mean, that's completely unusable. So we switched over to jemalloc. It totally solved the problem. Apparently, this has been fixed in newer versions of glibc, but we haven't looked back. Kind of a similar story with Haystack, where the index loading sped up from 4 to 10 times. That's wow. And the 10x number is for an actual production data set, whereas the 4x is for just a test data set. Then a couple of query servers that we've switched over. The first one we were using glibc. We tried tcmalloc and jemalloc. tcmalloc appeared to still have some fragmentation issues, so we used jemalloc, 30% improvement in throughput. And then had another one where tcmalloc was causing us fragmentation without band, and switched over to jemalloc and got a 10% throughput improvement there. Okay, a couple items for future work, and then we're about done. So arena management has been kind of a difficult thing to get right in jemalloc. I've messed with a lot of different algorithms for rebalancing how threads are associated with arenas over time. You know, if there's contention on a lock for an arena, try to shift some of the threads over to different arenas, that sort of thing. And really, I've met with a lot of failure in this regard. But still, I think jemalloc currently is a little overly simplistic in how it does its round-robin assignment of threads to arenas. We need to adapt it so that it pays attention to how many threads are currently using each arena. Potentially, if there are no threads using an arena, change its dirty page purging threshold to 0, or migrate those chunks over to another arena, something along those lines. So there's a lot of room for improvement here. For most of the applications we're using it with, we just don't see any problems where this would change anything, but there are some situations where you have an application that uses a bunch of threads to load data in and then switches to a different mode of execution after that, and some weird things can happen with thread assignments that cause some problems with fragmentation. And then a couple of other possibilities. Somebody right ahead. Now that the locks have been pushed down to the bin level for the arenas, it might make some sense to segregate arenas so that some of them handle small objects and some of them handle large objects. And something to play with. I don't know if it's actually going to be very useful. And then, you know, it sounds crazy to put a web server inside of an allocator, but really the only reason I haven't done it so far is because Facebook already has all the infrastructure for being able to get at the internals of jemalloc at runtime. So as crazy as it sounds, it's a real prospect. And then maybe not so real as embedding an email client. No project's complete until you've done that. Okay, I want to thank a bunch of people. The people at Facebook that have especially been helpful to me, you can see their names here: Keith, Andre, Jordan, Mark, and Paul. There have been a lot of other people that have contributed in a number of ways, both at Facebook and elsewhere. Mozilla has been really helpful over time, FreeBSD project, and a lot of other people. I mean, I'd have to have multiple slides to name all the people that have helped me. So.